Hello everyone, uh, welcome to another video. I hope you're doing well. For those of you who were fasting in the month of Ramadan, happy Ramadan. Today I will talk about univariate analysis and what univariate distributions are and the shapes of distributions are. Uh, as I mentioned, as I discussed in my previous videos, that we're mainly looking at three types of analyses when it comes to variables. There's univariate analysis, there's bivariate analysis, and multivariate analysis. Univariate analysis involves working with one variable at a time. And bivariate analysis when you're looking at two variables. So an example of bivariate analysis is t-test, or when you're testing relationship or significance between two variables, between two categories of variables. Multivariable analysis is when you have multiple variables included in your analysis, such as multiple regressional tests. Today I'll start this section with univariate and start with the shapes of distribution, univariate distributions. It's very important to familiarize yourself with the shapes of distributions because it's a good start point. When you are looking at a data, instead of looking at a crosstab, I think it's a very effective practice to start your analysis by looking at the shapes of your distribution of your data, and this allows you to look for any abnormality, any trend, any skewness, and that not only helps you in terms of deciding what the right analysis is, it also it also helps you to use the most effective way to start your statistical test, at least to be able to test their normality. So in our case, let me go to my PowerPoint slides. There are a series of distribution shapes that I will show you today. I will start with unimodel and bimodel. So as you can see, unimodel is the sort of type of distribution where the distribution is clustered in one model. Unlike the bimodel, the distribution does not have two models within it itself. While in a bimodal distribution, you see two models. As you can see, the first model being here, second model is, or a chunk. There are two chunks within a distribution. And this one, a unimodel, is one chunk distribution. I think a easier way to put it is like one chunk distribution, two chunks distribution. So I know when you read through the academic texts or materials on what these distributions are, a lot of you'll find a lot of materials difficult to understand because they don't provide like very practical examples. But I think it's a better way to learn statistics is not to only rely on the text, but also look at the practice side of those and try to relate each statistical instructions with a practice and try to put it into a practical context to give you more sense. So if I were to use an example in a unimodel distribution, I would say anything, for example, age could be a good example of a unimodel distribution. For example, if you were to look at the age of, let's say, everyone in India, so we will see that the age distribution will go from 0.1 year old or 1 year old to maybe 150. So the biggest chunk of the distribution will be in the middle because this is where the majority of the ages are, which may be between 20 to 60 or 30 to 50. But in a bimodel, age may not be a good example because it's not like everybody will be either 20 years old or everybody will be either between 1 year old and 20 years old, or either people are between 40 years old or 60 years old. Only a very small fraction of the population is, let's say, between 20 and 30 years old. So a bimodal distribution is not a good example. Age is not a good example to explain a bimodal distribution. Rather, a good example to explain a bimodal distribution may be maybe wealth distribution in a society, where you have one chunk of the population has majority of the wealth, and then there's a very small middle income, and then another chunk of the population has, you know, the other majority of the wealth. Uh, However, in most cases, it goes from the lowest all the way to the highest with an exponential growth. But it could also go from, let's say, if we were to say that a big chunk of people, let's say between the ages of 1, and 20, or economically prosper, and then somewhere in between, people are not economically prosper, or they're not. There's a very minimal middle income, and then there's a huge, rich, population fraction. That could be a good example of a bimodal. But anytime that you populate your distribution in terms of a chart, or when you plot them on a chart, and when you see that your data points go from like highest, and then it goes down, and then it goes back up again, then you're looking at a distribution that has two models. The next one is the symmetrical distribution. So symmetrical distributions are pretty much the opposite of bimodal. It's a unimodal distribution, but it's symmetric. In other words, it's a bell curve shape, as they call it in textbooks. Yeah, so meaning that in symmetric distributions, and this is why, as I said earlier, it's important to know your distribution shape, because it designates what type of test you're able to do. Because if your shape is not symmetric, let's say it's asymmetric, then maybe a parametric test is not the suitable test to do for that distribution. Otherwise, you will not have accurately, effectively drawn conclusion. So a symmetric distribution may be, again, let's say IQ. So an IQ could go from people with the lowest IQ maybe here, and then people with the biggest chunk of people will be somewhere between in the average area of the IQ, but then there will be a small fraction of people who have the highest IQ. So a lot of data, a lot of statistical information are symmetric by nature. They can never be asymmetric. For example, IQ, because there's already a designated standard. Those numbers are standard, and also even by common sense, we won't have a big chunk of people having the lowest IQ, and then a very small fraction having the lowest IQ. So it's most likely that a big chunk of the people have average IQ, while a small fraction of people have either low IQ or the highest IQ. So symmetric distribution. Again, if you ever, if when you plot your distribution, and you see a shape like this in an histogram, then you're looking at a symmetric distribution. While on the other hand, as I just explained, this is asymmetric distribution. That's shape skewed to the left, meaning it's it has a long left tail. For example, let's say in the case of IQ, as I said earlier, it's not like a lot of people have lowest IQ, and then most of the IQs or a majority of people have the highest IQ, and a very small fraction of the people have the lowest IQ. That's obviously not how. That's at least not how it is, because I don't say that people have lowest IQ overall, but I'm saying that people have on average IQs. The majority of people have average IQs. Or a distribution could also be skewed to the right, where we have everyone is have the lowest IQs, and then a small like fraction, like a small, very marginal fraction of people have the highest IQs. So this skewed distribution, left having a left tail, right having a right tail, are also indicators that your distribution is not normal. It's not symmetric. It's not normal curve shape here like this one. So this also designates. This also helps you to designate what type of test, statistical test, may be the most appropriate test to use to do a univariate analysis. And then also this is clustered, and this is with the gaps. So again, any distribution where the information are clustered within one group, and then sometimes you have distribution where you have a gap. In this case, where there's no records, there's no scores for, in this case, going from 30 to 100 between 77 and between 97. So this deviates from the rest because this value or this score or this data point is actually a deviation. It's an outlier. So if this outlier is removed, then this will not be a distribution with a gap. It's almost it is a cluster. It will be a cluster distribution, but it will be almost a, a normal curve, a symmetric distribution. So I hope that these distributions were helpful, and these shapes were helpful, and also the examples I provided were helpful in understanding what the distributions are and what exactly they imply in a statistical context. And I hope this video was helpful overall. Thank you so much.